All right. So we were talking about this system, very simple system, one single machine connected to an infinite bus through a line. We're going to use this data for other cases that we're going to discuss today. The first part here was to discuss what are the equilibrium point for this system and to anticipate what is the behavior of the system around those equilibrium points. So we calculate the two equilibrium points, and we are going to have infinite solutions. So we're going to focus between 0 and 2 pi, 0 and 360 degrees. And then the linearization of the system, we get this linear model. We replace in the two equilibrium point between 0 and 2 pi, and we get the description of the system. The first equilibrium point with an angle delta between 0 and pi over 2 will be a stable focus, as we can see here by the eigenvalues. And the following one, the one that is between pi over 2 and pi, that is going to be a saddle node. And that's what we did. And then we talk about how we can do this in Matlab, and I put the code in Canvas, so you can download it and play with that. But I also want you to get good at programming this, because we're going to work with all the system we're going to deal later with multiple machines. We're going to use a similar code. But here's a sketch of what we're going to do in that code. And I put 6 steps. The first one is to define data. And then we're going to calculate the initial condition. If we don't have any disturbance, and today we're going to talk about disturbances, but if we don't have any disturbance, probably we can use the equilibrium point and shift it a little bit in some direction. But we're going to talk today how we can describe a disturbance in our model. And then we need to define the parameters of the solver. So there are some parameters like the maximum time step we will take in the solver. We didn't use it last time, but we can specify that if we want. Another parameter we need to define has to do with the time. What is the window of time in which we're going to have this simulation? Step 4, we invoke the solver, and that is the typical extractor. We can use different type of solvers. And in particular, later, we're going to deal with differential algebraic models. So in that case, this solver will not work. So we need to use OD23T or OD115S. But we will talk about that. There are different solvers we can pick from Matlab. And when you invoke this function, then you need to specify what is the set of equations we need to consider for the system, and the window of time in which we're going to have the simulation, and the initial condition for the simulation. When we do this, we use this handle function, and we have to specify the function f either at the bottom of your code, or you create an m file with the same name, in this case, f.m. And in this function, we're going to define the set of equations we need to consider for the system. When we do this, then after you invoke the solver, you will have the solution for t and x, and then we can plot the result. And don't forget that t is going to be a vector, column vector with the time, different time at which the state variables have been calculated. And x is going to be a matrix. Each column will correspond to a specific state variable. So we did that. We have a Matlab code, and these are the results we got. So because we didn't consider any disturbance yet, we used the equilibrium point, and we shifted the equilibrium point a little bit. In this case, instead of having a frequency of 1 per unit, we consider the frequency 1.02 per unit, a little bit higher in frequency. When we do that, then that's the evolution that we have for the system. We also got this plot, which is in the phase plane. You have the angle and the speed of the machine, and we started from this point, and you can see that the system converges to the equilibrium point, which is a stable focus. At the same time here, and we didn't do this, but I plot the eigenvectors of the second equilibrium point, which is a saddle node. So here we have two equilibrium points, two eigenvalues. So the eigenvector related with the stable eigenvalue is this one, the eigenvalue that is real but negative. So if you get close to this eigenvector, the system will be pushed towards the equilibrium point, which is a saddle node. And the other equilibrium, the other eigenvalue will be associated with this other eigenvector, which is the unstable one. This is the eigenvalue real but positive. So if you get close to that eigenvector, you will be pushed away to infinity, either in that direction or that direction. So that's what we did. Something that I didn't mention is that certainly you have oscillations here. But here the oscillation, we can see how much is the period. If we have the computer in Matlab, maybe we can look at this. But here you can kind of estimate what is one period and determine what is that time. Based on my appreciation of this plot, probably this is a little bit less than 1 second. So the period of the oscillation is less than 1 second. The frequency is a little bit higher than 1 hertz. That frequency will have to do with the eigenvalue that we obtain for the stable focus. So if you take this number, this is radians per second. If you take this number and divide it by 2 pi, you will get the frequency of the oscillation. So that is, let's check. I have Matlab right here. It went away. What is the value? Do you remember? 8.7. Here it is. 55. So if we take that value, the imaginary part of the eigenvalue, and divide it by 2 pi, then we get the frequency. And the frequency is 1.39 seconds. No, that's the frequency. So 1 over that will give you the period, which is 0.7 seconds. So that's what we should, this is a linearized representation of the system. It's not going to be accurate. But if the system is very close to the equilibrium point, these should be very close to the frequency and the period that you observe in the simulation, okay? We will play with the code in a little bit, but I want to mention that this is radians per second. You divide that by 2 pi, you get the frequency in hertz. And that's what we should observe here. These should be about that frequency. And the period of these should be about 0.7 seconds. What else we did? We tried different initial conditions. If for some reason the system was disturbed a little bit farther, what can we get? And I have the plot well done this time, and this is what we get. So now, instead of starting here, we're going to start a little bit higher. This was, the frequency here was 1.02 per unit. Now it's 1.042 per unit, much farther from the equilibrium point. So what we get there, we see that we still have a stable system. The trajectory gets dangerously very close to the eigenvector here related to the saddle node, but still doesn't cross that eigenvector. And when we get closer here, we're pushed away from that saddle node, and we return to the stable focus, and the system stabilizes again around the equilibrium point delta 0 in a frequency of 1 per unit. That's good. And we go a little bit farther. Yeah, we can try different values, and that is the other case. Now we move a little bit, 1.043 instead of 2, 3. We move it a little bit. There it is. We move the initial value, and this is what we get. The trajectory at some point when this is a linearization, which is going to be very good around the equilibrium point. So at some point, we cross that eigenvector, and we are attracted by the unstable mode, and we're pushed to infinity, and the system becomes unstable. Yeah. So this is what we observe. Look what happened with the angle. Get from the equilibrium point delta zero that we obtained, go to around 40 radians, which is pretty high. And this is what happened to the frequency. Do you think that after a while the system got stabilized or not? What do you think? Based on the plot that we have. It seemed that got kind of stabilized, but look at the frequency, it's still oscillating. It's very strange. And now a question for you is everything fine if we let the machine go from this angle to an angle that is about 40 radians?
Well, I mean, yeah, because, well, as long as nothing critically messed up in its transition to there, then yes, because it's just a little bit further ahead in its cycle now. Mm-hmm. It's like a few
days. We might expect that. What do you mean by what you said? If nothing is messed up or strange or off, what do you mean by that? Like, what do we need to look at?
So like, if you were, example, swinging a pendulum, right? And it's supposed to go back and forth, and then suddenly something knocks into it and it sends it spinning every once in a while, or like for a while, and then it eventually starts returning to a steady state. It will be functionally the same steady state, but just it went in a few more circles than it was intended to.
Yeah. That's a good observation, and that worked very well for the pendulum. But in the power system, we need to look at what is actually happening with the electrical variables. So what happened when the angle going to go 2 pi ahead, or maybe 4 pi ahead? What would be that problem? So we'll go back to the circuit. So where is the angle in the circuit? Oh my, there it is. So this angle will go all the way plus 2 pi or 4 pi, 6 pi, whatever it is. And here you have an infinite bus. What is the angle of the infinite bus? 0. So we have an initial angle. What is the initial angle for the? We put numbers somewhere here. There it is, 0.24 radians. Yeah, that's the equilibrium point we got for the system. But if we look at the circuit, initially you have 0.24 radians here with respect to 0. What about if this go 0.24 plus pi? What would happen in that case?
That would mean that there's a lot more voltage pushing it around that way. So you're going to have
voltage that will fall across these impedances. And what will happen in that case?
The power lines are going to draw a whole lot more current than they were intended to handle.
The impedance is the same. If you have a large voltage here, what will happen? Huge current. And what is the period of the duration of this? We look at the plot here. There. From here to here, let's say 3.5 seconds. For 3.5 seconds, you will have something, a current that is very large. So that will not be possible in the power system. If that happens, this will lead to very high current, and the protection scheme that we have in the system will react and start disconnecting components, because it will be as if we have a short circuit in the system. Yeah, we don't have any short circuit. We haven't talked about short circuit yet, right? We're just play with the initial condition, but we're going to have very large current. What I'm going to ask you with the code, get the magnitude of that current, and also get the electrical power for that case when the angle go into that excursion. Yeah. What we're going to see, do you think we may have negative electrical power coming out of the generator? We might. What is the meaning of a negative electrical power coming out of the generator? It's behaving like a motor. It's absorbing power from where? From the infinite bus. So if that happened, we will have that situation, and that can be very dangerous. Yeah. So we will take a look at that. Play with the code. I left the code in Canvas, so you can play with that. Now we're going to add a little bit more of information and practical description of the dynamics, and we're going to talk about disturbances. What can make the power system deviate from the equilibrium point? And we are going to have different disturbances. One can be changes in the load. Yes?
Sorry, but talking about before about the generator taking on a motor behavior when power becomes negative, is there any like historical, like actual instances of that like happening? And then
Well, we're going to look at a paper from 1997 maybe, or 96. There was a huge blackout in the West Coast because of the system was subject to severe oscillation that later lead to the blackout. So there we have practical information, and that is reported in a paper. So we will take a look at that situation. In this case, because this takes so long, protection should act very quickly. Just a few cycles of the signal. How much is the AC signal in the country? 16.67 milliseconds. There's a few of those, 3 times of that, or maybe 5 times. They're very quick. We're not going with, if we have a real system and you have protection scheme, we will never let this happen. The system will be interrupted way before that because of the danger of this very high current in the system. So, as I said, we're going to add some more description into the dynamic behavior, and what is going to lead to this oscillation in the system are going to be the disturbances. And the disturbances can be a failure in a power plant, as we showed at the beginning of the class. There was a fire in some substation in Florida that led to an event, and the machines in the eastern interconnection started oscillating. So it can be that, it can be fire, it can be changes in the load too. But the most typical one are going to be short circuit. Okay, and short circuit can be of different natures. The system is an ABC system, 3-phase system, 3 phases. So when you have a short circuit, a typical short circuit might be maybe a storm. You have a storm, and the branches of a tree fall into a line, and the branch will make contact with the 3 phases, and you have a 3-phase short circuit. When you have that situation, a huge current will go through the branch that might burn the branch, and it might fall to the ground. And after a while, you don't have any fault whatsoever. In that case, we will say that the fault is self-clear. The fault remains for a fraction of a second, and it's removed itself, self-clear. But we may have vandalism. Someone with a change might go, crazy at night maybe and throw a change in the transmission line and create a short circuit. You might have huge current, but probably that short circuit will remain there. And we need to do something. What will happen? That probably the protection scheme that we have in the system will try to isolate that fault. For that isolation, we require the disconnection of some components. So if this happens in a transmission line, the transmission line will have on the ends, on the extreme of that line, breakers. So if the protection scheme detects that there is a huge current, will open the contact on the extreme and isolate that fault. So that's another type of fault, a fault that requires the disconnection of some components, and we isolate that fault and we protect the system. So we have these 2 choices. The fault also can involve not just the 3 phases. It can involve 1 phase, or 2 phases, or 1 phase and neutral, or ground, or any other combination. Because this course is based on a balanced operation, we're going to consider just balance operation in this course. We're going to assume for the application of the dynamic analysis, we're going to assume that we just have three-phase short circuit. Three-phase short circuit, like what I have here in the diagram, is going to affect all the phases equally. So if we have a three-phase short circuit here, the current at default in phase A, B, and C are going to be balanced. What is the meaning? They have the same magnitude, and the angle between the three phases are going to be shifted 120 degrees. That's a balanced short circuit. And we're going to consider just that case. As I said, it can be just a short circuit between phase B and C. So we don't have any contact whatsoever with the phase A. What is going to be the short circuit current in phase A in that case? 0. There is no short circuit. But what is going to be the short circuit in phase B and C? The same magnitude, but they're going to be shifted 180 degrees. As you can see, that is not going to be a balanced short circuit, and we're not going to consider those cases here. Yeah, just three-phase short circuit. And example C. Now we're going to have something more realistic, and we're going to program this and see what we obtain. We're not going to play with the initial condition and put any number that we want, but we're going to deal with a short circuit. So in this case, we're going to have a short circuit at bus 1. So this bus is going to be with a short circuit between phase A, B, and C, a balanced short circuit. During the short circuit, this is the circuit that we obtain. Basically, we're making the voltage at bus 1 0. Yeah? If the voltage at bus 1 is 0, then we can inspect this circuit and see how much is electrical power that will come out of that generator. Because we need the electrical power because that defines acceleration in the machine. Can this fault be isolated? If we have a fault here by bus 1, can we isolate that fault? What do we need to isolate? Imagine we have a protection scheme and we have breakers somewhere.
You isolate the generator from the rest of the
infinite
bus.
You isolate the generator from the infinite bus, and then it's pointless for us because we're trying to understand the behavior of that generator. Yeah? So the only way if these remain in the system will be to open the contact of this line and isolate the generator. You will not have any fault, but this generator will be disconnected. We're not going to consider that case, of course, because we're interested in the dynamics of this generator oscillating with the infinite bus. So our assumption here is that the short circuit is going to be self-clear. It will remain there for 0.1 seconds, and somehow it will disappear. What is another example of a self-clear fault? You have seen that. It's kind of sad, though.
A squirrel.
A squirrel. You might have that, or a bird. You know, those things can happen too, sadly. Yeah, so during the short circuit, that's the situation we have. And because voltage and current here from the generator and voltage at the grid, I said, they can change instantaneously. We are assuming that the energy involved with those variables is 0. Therefore, this variable can take any value immediately, and that will happen with the short circuit. We have a short circuit, the voltage will set to 0 immediately, and this current will change from whatever current we had before the fault will change to whatever current we obtain now. If we look at the circuit, the current here, because the voltage here is 0, is defined by this voltage that will completely fall into the internal impedance of that generator. So this voltage divided by that impedance will give you the current. And that's what we have there. The electrical power that comes out of the generator is voltage multiplied by this current conjugate. So we replace that here And as you can see here, the exponential j delta get canceled with the exponential of negative j delta, because this is the conjugate of the current. So these terms get canceled. Basically, you have here E squared, and the impedance is negative j xs. 1 over negative j is just j. And the real part, because this is a purely imaginary number, is going to be 0. In this situation, then, the electrical power that comes out of the generator is 0. So what is the problem with that?
Mechanical power is going to be more, so the generator is going to accelerate.
So the mechanical power, we have an assumption here, because we're not considering the governor. The assumption is that the mechanical power is fixed for whatever operation we have in the machine. If all of a sudden, the electrical power that was equal to the mechanical power, now all of a sudden the electrical power becomes 0, you have full mechanical power speeding up the machine. And what we're going to expect, well, the speed will increase and also the angle delta will increase. And that's dangerous. So this is the situation. You have the electrical power here in blue, you have the mechanical power in red. The intersection of those two characteristics will give you the equilibrium point. Here is the subtle node, but we're assuming that the system is operating at the stable focus. That's the angle for the equilibrium point, and the speed has 1 per unit. That's the value of the speed. So the system is operating at the equilibrium point, but now we have a short circuit at time 0. What happened during the short circuit, the electrical power immediately is sent to 0. Immediately. It's an algebraic variable. Immediately. But because delta is a state variable that is involved with some energy stored in the machine, then this angle cannot change instantaneously, right? So when this happens at time 0, the angle doesn't change. That's a state variable, but the electrical power changes immediately. PM is the accelerating power in the machine. The machine will start speeding up. The speed and angle will start increasing. So if that is remaining in the system, this angle in the machine will start increasing. So we will move with a 0 power output from the generator. We will move to the right. Until when? Until time TCL, the clearing time. In this case, is 0.1 second. At that time, the fault is clear. So the machine will start increasing the angle and the speed until this point, and all of a sudden that fault is clear. So when that happens, at that time, the electrical power is restored. The system goes back to the initial configuration, and all of a sudden now the power moves from 0 to whatever value we have here. This is the electrical power. What is going to be that electrical power? Because the angle cannot change. This is state variable. This angle in the machine, at that time, after we clear, the fault is clear, will remain the same. So the electrical power will jump to this value. What is accelerating power now? PM minus PE. It's going to be negative. So the machine was speeding up, but at this point, we're going to apply this acceleration. This increase in the speed will start becoming smaller and smaller until at some point the angle will stop increasing. We will have that situation. If the machine stops at this point, the angle will not increase anymore because the acceleration is still negative. The angle will start decreasing. When we arrive to that point, the accelerating power is 0, but we have some inertia. The angle is decreasing, so this will continue decreasing. When we move in that direction, what happened now with the accelerating power is positive. So that will start, that decrease in the speed and the angle will be stopped because the accelerating power will become positive here. And at some point, that angle will stop decreasing and will start moving in the opposite direction. And the machine will oscillate until we converge to the stable focus. Yeah. So that's the situation.
Quick question on that figure. So the reason when the fault's cleared, the reason the machine continues to accelerate back again is because of the
Inertia.
energy stored.
Yeah. So the machine is increasing the speed and you have an inertia. And when you change the accelerating power, that will not change immediately. You have energy. So that energy needs to be reduced and will be reduced by the negative accelerating power. And it will take some time depending on the inertia of the machine. Yeah. So what we're going to do now, we have a code. We're going to play with that code. Yes?
So when it gets to the maximum angle, it doesn't continue on the trajectory, it turns around?
Yeah, from here, the accelerating power will be 0 because it's PM minus PE. That will be the case all over this area. But because you have some inertia and the machine was increasing, it will continue the increase until this point. At this point, the machine will reach the maximum angle and will start moving in the opposite direction.
And I guess if the fault wasn't cleared in enough time and the machine gained too much acceleration and it pushed beyond the other point, then we lose stability.
We lose stability. And that's what we got before. Yeah. So the only difference that we're considering now is the short circuit. We're not going to apply an initial value willy-nilly. No, we're going to simulate this short circuit and see what is the initial condition after we clear the fault. So when we clear the fault, what is the initial condition? We're going to simulate that. So let's talk about the initial condition. So you have two simulations. One simulation is when you have the fault. What is the accelerating power in that case? PM, because electrical power is 0. So we need to simulate that case and see and determine how the angle and the speed will change until this point. So we will simulate this part. At this point, what we're going to do? The state variables cannot change instantaneously. The angle and the speed will be the same. So the fault will be clear. The electrical power will be restored. The accelerating power in the machine will change. But we're going to use the state variables at the end of the short circuit as an initial condition after the fault is clear. So we will simulate here two parts. During short circuit, we will get the value of the state variable at the end of the short circuit and set that as initial condition at the beginning of the system when the fault is clear. Yeah? So that's what we're going to do. And these are the steps, and we will work on Matlab now. The steps are similar to the one that we used before. We will define data. Then we will calculate the initial condition. Now, because the disturbance is going to be modeled through a short circuit, the initial condition will be exactly the equilibrium point. We're going to assume the short circuit is at time 0, and then we will define a clearing time. This is self-clear at time 0.1 second. We will define the solver parameters. Maybe we can define a maximum time step, but we also need to define the time. So the time of simulation of the short circuit is going to be between 0 and the clearing time. When we define that, we can invoke the solver. We're going to call these T1 and X1. That's during the short circuit. OD45, that's the solver we will use. And we need to define the equations during the short circuit. What are going to be the equations? For the angle, it's going to be the same. Omega multiplied by omega minus 1. For the speed, the derivative of the speed in time is going to be what? The electrical power is 0. What is the accelerating power? PM. PM divided by 2h. That is the derivative of the speed during the short circuit. The time is going to be 0 to 0.1, and x0 will be the initial condition, the equilibrium point. And this function needs to be defined at the bottom as a subfunction or in a separate file and need to have the name fsc.m. When we get the solution, MATLAB with the solver will give you the solution for this. The first column is going to be delta, second column of x1 will be the speed. We look at the last row because that's the last time, 0.1 second. On the last row, we will have the state variable, the value of the state variable at the end of the short circuit. We will take that and store as the new initial condition for the next simulation. What is the next simulation? We will store the variables T2 and X2. That is the case when the fault has been clear. What are the differential equations? The same one that we used before. Now the accelerating power is going to be Pm minus Pe. The time, we need to define the time. The time will be from 0.1 to whatever final time we want to simulate, maybe 10 seconds, 20 seconds. And the initial condition, that is the last point that we have during the short circuit. We solve it, and we have the solution when the fault has been cleared. Because the time moves in a sequential fashion, first is short circuit, the last value here is 0.1, and the first value here for T2 is 0.1, we can concatenate the result by doing this. We put them consecutively. First, the time during the short circuit, and then the time after the fault has been cleared. The same thing for the state variable, and the result will be in T and X. As I said before, these two functions, during the short circuit and after the fault is clear, need to define as a subfunction. Yeah, so we will work on that. This is the code we got before. There it is. And we put the data here. We put the data there, and this is in Canvas. Then we calculate the equilibrium point. We set the initial condition. We move the equilibrium point along the speed, and we solve it. When I was doing this, then we didn't do this last time, but you can check this. Basically, for that equilibrium point, I am getting the eigenvalues, and I am plotting the eigenvalues around this saddle node. And those are the segmented line that you saw in the slide. And the subfunction was here. But what is the issue that I tried to play with this and I found an issue? That I have the data twice. I have the data in the subfunction, and I have the data right there at the beginning of the code. So that's not a good idea. You need to have just the data in just one part. So what is the best way to do it? Just define a function with the data, and that's what we're going to do. So you will go to just one point and change the data in that only part of your code, okay? What was the issue here? Start playing with the power. You see the power is 2. Our initial mechanical power was 0.5. And I said, well, let's see what happens if the power is 1 per unit, or 1.5, or 2. And I couldn't see any difference. And the reason was because I was changing the power there, but not here at the bottom. So let's not duplicate the information. And what I did, I create a version 2, right there. As you can see here, I created a function that will load the data. So where is this set function? At the bottom of the code. So we have a set function that is called data. You just call that and we'll load all the data that we need. So let's use that from now on. All right, so that's the code. What I'm going to do here, let me run this and see if everything is fine. Yeah, that's the case that we simulated last class, but now we're going to change it. So what we're going to improve now is the initial condition. This initial condition will be determined for the simulation during the short circuit. And that's what we need to change now. So what I'm going to do here, I'm going to use the same file, but I'm going to save it with a different name. So this is going to be example C. Yeah. So the example C will consider the short circuit. The data is the same. The equilibrium point is the same. This initial condition is not needed anymore. Well, the initial condition will be exactly the equilibrium point in the system. But at this time, we're going to define the disturbance. The disturbance will require the time TCL, the clearing time. And we can define this as an input. So input, enter, clearing time in seconds. So we have that. And we have that as an input. There. So when we have that, critical clearing time, not critical, clearing time, the time for the solver, we're going to simulate the short circuit now. It's going to be from 0 to the clearing time. Here, when we invoke the solver, this needs to be a different function. Is the differential equation during the short circuit. And these need to be defined at the bottom. So here we have the differential equation when you don't have any short circuit. So we will create another one when we do have short circuit. So the name for this is during short circuit. The name for this is going to be FSC. The data is the same. The variables are placed in the same order. The first one is angle delta. The second is the rotational speed per unit. So the difference here is going to be the electrical power. The electrical power, this now is going to be 0. Yeah, so if that is the case, this is going to be the damping force, and that's a mathematical definition, and that's related to the dampers that the machine might have. We can leave that there for now. So we have the function during the short circuit, and after this, you're going to get the solution during the short circuit. And now we need to repeat this, and as we said, we're going to call this T1 and X1. When the fault is clear, the state variables cannot change instantaneously. So the last value of the state variable X1, which is in the last row, and all column, that's going to be the initial condition for the system when the fault is clear. The state variable need to start from that point. And then the time will be different now because we're simulating this from the clearing time to some final time. How much did we use last time? 10 seconds. Let's put 10 seconds there. And then we invoke the solver again. But in this case, the system is restored and we use the differential equation when the fault doesn't exist anymore in the system. This state, the state variables and the time for this part is going to be T2 and X2. Here, we're going to concatenate results. So the time that we are going to have now is T1 is a column vector, and below that we put the second vector of time. For the state variables, the same, we put the matrix X1, but below that we put the matrix X2. And now we have the variables T and X. So let's cross finger and let's see what we get now. Save. Let me close all figures and we ran it. Enter clearing time. I said 0.1. What? Well, there is something off.
Looks like it's just a short circuit.
Yeah, after that, it doesn't do anything actually. So we need to check what is the problem with this. So the issue here has to do with the simulation of the second part. So we do have the short circuit, and that seems to be working fine. This part is working fine. But this part is working not fine because I didn't change the initial condition. I was having the same initial condition of the stable focus, and the system just went there straight. No, the initial condition need to be the last value we get when the short circuit was present in the system. So let's see now. Close all, and we'll run it again. We have to enter the clearing times, 0.1 seconds, and now we're talking. So as you can see now, we're still far away from any critical behavior, but now we have something more realistic. So what is more realistic? You have the equilibrium point in the system, but what moves the system away from the equilibrium point is the short circuit. So the short circuit remains from 0.1 second, and here the fault is clear. The state variables are not far away from the stable focus. So the system, the trajectory is attracted to the stable focus again and converges to the equilibrium point. Everything is fine. That's the evolution now of the state variables. But we can play with this. We can run again. We're going to put a very high clearing time just to see what happens. Half a second. That's not normal. We will never have a fault that lasts that long in the system. But for the purpose of the simulation, then we obtain this. What can you tell me? What is happening here in the system when we let the fault remain for so long into the system? What do you think? You have the equilibrium point. The system now is subject to a fault. The angle and the speed start increasing. We are not clearing the fault. At some point, we clear the fault, but it seems that it's too late. We have crossed the eigenvector related to the stable eigenvalue, and now the system trajectory is trapped in this region in which we will have the force of the unstable mode, and we're going to be pushed to infinity. What can we say about this behavior? We're talking about the clearing time. We're talking about how much we're going to let the fault be present in the system. And from this situation, we can anticipate that here, there must be a critical time to clear a fault. This is a very simple system, but we can play with this, and we're going to talk about this soon, but we can play with this and try to find that critical clearing time. So we use 0.5. What about if this is 0.45 seconds? Would the system be fine? Yes. So based on the system that you have, there must be a critical clearing time that you need to consider. And when you have your protection system, you need to program your protection system so the fault is clear before the system go into some instability, and the trajectory will be pushed to infinity. Yeah. Typically, as I said, the fault in the system are clear very quickly. It's a matter of a few cycles, 5 cycles, less than 0.1 second, and the fault is going to be clear in the system. The system with more machines and a different topology, of course, will behave different. This is a single machine infinite bus. So in this case, it seems that the machine can withstand a fault for a longer time. What I'm going to ask you, well, I asked you at the beginning, play with the system that with the code we had before. What can you play with? You can play with the mechanical power. Are you going to have the same behavior if the mechanical power is increased a little bit? How much is the mechanical power now? 0.5. What about if the mechanical power is 1.5? Will you get the same behavior? What about the critical clearing time in that case? Is it the same if the mechanical power is 0.5 or 1.5 per unit? Let's play with that and see what conclusion you get. Yeah. Thank you, guys.